the last module we were working on was basically the numerical solution of ordinary differential equations, which is a very big topic in computational physics. We looked in particular at the solution of the damp-driven pendulum. In this module, I want to move on to the numerical solution of Fourier transforms. That's also a very big topic in computational physics. And one of the examples we use here too is the damp-driven pendulum that we've already met. So basically, we're moving on from ordinary differential equations, then numerical solution, towards Fourier transforms and their numerical solution. You've probably seen a plot like this before. You've probably worked with a plot like this before, but just to introduce the idea, the concept of Fourier transforms, and maybe I'll say Fourier decomposition. So in this particular plot, we look upstairs here. Imagine you've got a square wave. So in black here is a kind of square wave, a rectangular wave that's repeating. The idea of Fourier transform, or the idea of the Fourier decomposition, is that that square wave, which is a discontinuous function, can be represented as a sum of many, infinitely many, continuous functions of sine waves and cosine waves, of sinusoidal functions. So that's the big idea, that we can break down, for example, a discontinuous function into sine waves, cosine waves of different frequencies. It's frequency components, basically. In this particular case, the frequency components of the square wave are shown in the lower plot. So there's a constant term, it's here. But then in blue, red, and magenta here are shown these three largest sinusoidal terms that together, if you add up this blue term and this red term and this magenta term, you get this red dash term that sort of approximates the square wave. And if we added in even more terms, higher frequency sinusoidal terms, we get an even better approximation of the square wave. And that's what the Fourier decomposition of a function like a square wave basically is. And so we're going to learn how to do this numerically. We're going to learn how to do this in Python, and we're going to use it for analyzing data. Just to give you a few basic facts about Fourier transforms, Fourier decompositions. So it's basically a math transform from for example, from a function in the time domain, a function that's a function of time, into a function in the frequency domain, where the function is expressed in terms of frequencies. Or it could be a function in the space domain, a function of spatial coordinates, and then it would be the Fourier transform would be a function in sort of spatial frequency. So maybe more generically or generally, we could say that that Fourier transform, that Fourier decomposition, it takes you from some configuration space like time or space to a reciprocal space like time frequency or spatial frequency. So that's what we mean by a Fourier transform, or a Fourier decomposition. It's this transform into this from a configuration space like time into a reciprocal space like frequency. It's interesting. I mean, we're used to it now. We just sort of accept it now. But when it was first proposed by Fourier, it was kind of ridiculed that you could do this, that you could somehow be able to represent a discontinuous function, say the square wave, by a sum of continuous functions, sines and cosines. So mathematicians at the time, famous one I think is Lagrange, another one is Euler, kind of ridiculed this idea that you could do this. But now, of course, it's established that you can represent a discontinuous function with this sum of many sine waves and cosine waves. So there's two ways it often gets applied. One where the function is kind of a smooth, say, analytical function, and you apply a Fourier transform and you get a smooth set of sines and cosines of continuous frequencies. And then the other one is where you have discrete data as your kind of your function. It's discrete data points, and you get a Fourier transform that's a set of sines and cosines, for example, that have discrete frequencies. So that there's continuous Fourier transforms and there's discrete Fourier transforms. So that's one pair of classifications. Another distinction is that sometimes we will decompose a function or data into sines and cosines, so those sinusoidal functions. Other times we'll decompose it into exponentials with complex exponents that are a function of a frequency. And that latter one is a bit more abstract to work with exponentials with complex exponents, to work with complex numbers, but it has some mathematical advantages, especially has some advantages when we're doing this computationally. And so that's a second classification. A big one thing that's interesting, you know, Fourier transforms been around for since the 1800s, but its widespread application didn't really take off, launch until sort of the 1960s, when a computer algorithm was developed for efficiently calculating Fourier transforms. And so this is a very famous paper by Cooley and one of the names Tukey, that I think they were both at Harvard and IBM, and they developed a very fast algorithm that suddenly made it possible to apply Fourier transforms for discrete data in all sorts of fields. So just this slide's a sort of advertisement for Fourier transforms. So one thing about it is actually nature does Fourier transforms. So your ears, how they work is basically they input sound, but they will decompose it into different frequency components, and then your brain, you know, perceives voice or music or whatever by processing those frequency components. So your ears are actually doing a Fourier transform. So nature does Fourier transforms. As I say, Fourier transforms are used across all of science and beyond. So they're widely used in physics and chemistry and biology, in astronomy, in engineering, in economics, in medicine. So it's very widely used. You see statements that it's the most powerful sort of mathematical tool that has been developed. It's so widely used. Famous sort of examples of use of Fourier transform are the discovery of the kind of the helical structure of DNA. That was due to Fourier transforms of X-ray data on sort of strands of DNA. So Fourier transform led to the discovery of that famous structure of DNA. Fourier transforms are the heart sort of sound compression and video compression. In medicine, sort of electrocardiograms and magnetic imaging, a lot of that's based on Fourier transform. So it's very widely used. Sort of more sort of mathematically, things like Dirac delta function, things like step functions. So Dirac delta function gets a rigorous sort of meaning through its Fourier decomposition into sinusoidal components. And it's something that's very important when you think about point masses and point charges, which are sort of basic to a lot of basic physics. Fourier transforms are also a very useful tool in solving differential equations. So you can transform your differential equation from, say, a time domain to a frequency domain, and solve them in that domain using sort of Fourier transform. So we're not going to talk about that, but they are used for solve as an approach, a method to solving ordinary differential equations. Okay, so now let's get on to a bit more of the details. So on this slide, I'm just showing, so I'm going to be worrying about discrete Fourier transforms of discrete data. So we've collected some data and we want to make a Fourier transform of that data. So that data might be as a function of time. Often it's a function of time. So in my examples, I'm going to think of it as a function of time, a function of some discrete time. So we're sampling some data at certain times. And then we're going to transform that into the frequency domain. And we'll also look at, you can transform that frequency data back into the time domain. So there's both kind of a forward-going Fourier transform and a reverse or inverse Fourier transform. So these two equations here, this upper one is the forward discrete Fourier transform. And this lower one is the inverse discrete Fourier transform. So let me just try and describe a few bits and pieces in these two equations. So it's because we're going to need to get used to them, or we're going to have to code them. So some of the things that are in them. So lowercase x subscript n. So maybe think of that as the time domain data. So we sampled some data, some information as a function of time, and we've represented it by an array x of n. So x0, x1, x2, x3, up to x of n. So that's an array of our time domain data. The uppercase x here with the subscript k, that's the data in the frequency domain. So that's also an array with those subscripts, uppercase x0, uppercase x1 through to uppercase x, the maximum value, and that's the data in the frequency domain. So these two equations in the forward case, right? They take the data lowercase xn from the time domain into the frequency domain of uppercase xk. And then in the lower k equation here, where we're going in the opposite direction, the inverse direction. So we're taking the frequency domain data. So that's x. I should have there's typo here. There should be a k. I'll fix that. X of k, uppercase X of k, into the back into the time domain. So those are the frequency and time domain data in those equations. You see that this is discrete Fourier transforms because it's a sum. It's not an integral. You see that in transforming the data from say configuration to reciprocal space or vice versa, you're multiplying by a complex quantity. So that's this exponential with an imaginary argument here, or this exponential with an imaginary argument here. So that's how the transform is accomplished. And if you look in the arguments, right, you see the indices of the domain that you're transforming from and the indices of the domain you're transferring to. So you got the product of k and n in the exponent here. You got the product of k and n in the exponent here. Couple of other remarks about these things. If you notice that there's a minus sign in the forward direction, but there's a plus sign in the inverse direction. So these factors are slightly different. There's a difference in sign. And then the second thing I wanted to point out and this is a convention how you do that. In the forward direction, I have no 1 over n factor here. This n's a number, uppercase n's a number of data points. In the inverse direction, I have a 1 over n factor here. So you need that normalization factor of 1 over n overall. If you were to go from time domain to frequency domain and then back to time domain and expect to get back what you started with, which is you should expect to get back what you started with, you need a factor of 1 over n in the normalization. And that's most often, I think, put in the inverse transform, but not always, but that's how it is here. Okay. So our job is to do that calculation from time domain to frequency domain or vice versa, numerically in Python. And our job is made easier in Python because and using numpy package, because that task actually is equivalent to multiplying a vector by a matrix to get another vector. So we're starting with a vector, which is the array, say, in the time domain. We're multiplying it by a matrix, which is the that product with that complex exponential. It has 2 arguments in it, the k and the lowercase n. Those are the indices of the time domain vector and the frequency domain vector. So it itself is a matrix of dimensions k by n. And so what that Fourier transform represents sort of mathematically to us and is useful in Python is that it's basically you're calculating a vector in the frequency domain from the product of the vector in the time domain and this complex matrix. So I just tried to sketch that out, that sort of way of picturing things in this slide here. So this lowercase x, right, and I'm now thinking it as a vector here with components I'm thinking of the uppercase X in reciprocal space here as also a vector, the same dimensions with these elements with the label. And then here's my matrix that represents the product with the exponent, with this complex number that's formed by an exponential imaginary exponent. I wrote out a few terms here so you could sort of picture what it must look like. So across the top row here, in that particular case, right, the value of, if we're going from time domain to frequency domain, all these elements have a value of k that's 0. And so it's the exponential to the power 0. And so all these guys are 1. So this top row of the matrix is just 1s. This left-hand column, likewise, this left-hand column corresponds to all the lowercase n's in indices being 0. So that also yields an exponential to the power 0. So all these guys are 1. Then all the other guys in this sort of quadrant here are basically have this sort of form here. So if we walk across this second row, in this first element here, little n was 0, so we just got a 1. Then we got little n is 1, so we just get this I to the times 2 pi factor. Then little n is 2, so we get a 4 pi factor. And so you get this pattern. And the next one will be minus I 6 pi over uppercase n, and so forth. And that continues on with the next row. So the next row, now the next row, k is 2. So everything from the row directly above is now multiplied by 2. So instead of a 2, we get a 4. Instead of a 4, we get an 8, and so on and so forth. So that's kind of the pattern of the matrix. If you think of that matrix, the absolute value of every element in that matrix is 1. It's just that is a different sort of mix of the real and imaginary parts as you walk through the matrix elements. So I wanted to make this plot, but I failed. If you think of the sort of complex plane, and think of a little arrow representing the length 1 matrix elements in here. So the top row, they're all kind of in the real direction. So they're a bunch of arrows going horizontally. If we start walking down the row below the top row, we got a 1, so it's horizontal, but then it starts ticking around as the exponent increases. And so you see kind of a phase rotation as you walk along that row. And then the next row, what you find is that you get a phase rotation that's going twice as fast. The next row even faster, and so on and so forth. So that's the pattern.